Many thanks for the invitation. I'm going to talk today about research that's been funded entirely by the Ireland Wales Regional Development Fund of the EU. And we're very grateful for this work going on over the last 9 years. But basically, what I'm going to talk about is this, and this is the variability in bacteria at beaches. And this work has been successful so far in improving the compliance rate of beaches in Wales. And we've now examined a total of 5 beaches. Now, this variability is expressed for the first site we did, which is Swansea Bay, which was very close to failure when we did this work. And each vertical line on the plot represents 25 data items collected at half-hourly intervals for 60 bathing days in the 2011 bathing season. And what is remarkable about this data is it shows as much as 1,000-fold difference between the samples taken on one particular day. Now that has great significance for the utility of what we call regulatory sampling, which in Britain is between 10 and 20 samples per year taken at maximum weekly intervals. We published this data in 2018, but we now have replication of the work at an additional 4 sites. Because when we did the Swansea Bay experiment, quite honestly, I didn't believe the results as the project lead in Wales. This project protocol was showing such vast variability every bathing day that it looked almost improbable. But Swansea's a very, very complex situation with 3 large outfalls, with 3 large rivers, with multiple inputs from urban areas. So it might expect to be a little more variable than other sites that were looked at. The second phase of work, which commenced in 2017, was at the 4 sites in Wales, chosen by the Environment Agency, by Dŵr Cymru, by our local authority partners, to be the riskiest sites in Wales, potentially, because they were all either declining in water quality or they were showing great risk of non-compliance. So the first site we chose was the northern site at Aberystwyth Bay, which was the only failed beach in Wales in 2016 and 2017. We commenced our sampling there using the Swansea Protocol, that's half-hourly samples for 12 hours a day, and we analysed every water sample in triplicates to get more precision. And we did this work at Aberystwyth in 2017. We had a model running in 2018, and the beach passed in 2018 and 2019 after failing for 2 years previously. Now, when beaches fail, they are at risk of what's called de-designation. That means putting a sign up saying bathing is not advised. And clearly for these coastal communities dependent upon recreation, that's a very serious impact on the local community economy. So this is why the work was done by the Regional Development Fund. And those are the 4 beaches on the slide there: Aberystwyth, Newquay North, Traeth Dolly, Traeth Gwyn, Newquay, and Nolton Haven. So all based on the Swansea Protocol, and that's written down there with half-hourly sampling, 25 samples a day, 3 days a week through the 20-week bathing season. It gives you about 1,500 sample results at the end of the bathing season. And the samples are analysed for Escherichia coli and intestinal enterococci, which are the compliance parameters required by the European Commission. And the detection limit for this work was 0.3 CFU per 100 millilitres. That means 1 in 300 millilitres. So the work is more detailed than is done for regulatory purposes. And the first question in our mind for this highly rural beach with about 150 population was, would it show much more uniform results than Swansea Bay? Because obviously that would be beneficial and give more credence to the regulatory sampling. In fact, it showed higher variability than Swansea Bay at the first site in 2017 examined, and we've now done 4 of these sites. At maximum, it showed 3.6 log orders of magnitude on a day. At minimum, it showed 2 log orders of magnitude. That's from 100 to several thousand-fold of variability every day. You can see that when we get rainfall expressed as the red line, which is in fact showing river flow, then the whole distribution seems to move up. But there's no less variability in a dry day compared to a wet day. The variability remains the same. And that's the intestinal enterococci plotted against the orange diamonds, which were the compliance samples taken that year. Now, remember, this was the worst beach in Wales. What that showed was that on the Environment Agencies or regulator, which in Wales is the National Rivers Authority data, 10 of the 17 items of regulatory sampling there show the minimum limit of detection, or lower limit of detection, which is 10, using the agency's 10-fold dilution. And 10 of the 17 were on the limit of detection, which suggests it's very clean. But if you look to the right, the one peak value, which was when a regulatory sample was taken late on in the bathing season, it almost exactly matched our sample taken at the same time, which was triplicate filtered and has a lower limit of detection. But that was the reason the beach did not pass in 2017. And that's a very, very common pattern for bathing waters throughout the United Kingdom. I suspect it would also be common throughout Ireland. We're both dealing with Atlantic, marine, tidal bathing waters. So there's no reason to expect this is not the same there. And that just shows the sampling transect for this Chemist Bay samples. And you can see the number of samples there. It wasn't really determined, it wasn't dirtier above or below the tidal limit. And the second site was in Cardigan Bay, Newquay North. And this, you can see the site here. It looks pretty tropical with the turquoise sea, but that's actually just a deposit of shells from a local shellfish processing plant. Data, again, highly variable, more variable than Chemist Bay. And you can see it goes from 2.3, which is several hundred log orders of magnitude every day, to 3.9, which is very close to 10,000. So the data is becoming to look as if that pattern is generic. And this, again, highly rural site, a small settlement affecting that beach in Newquay town. That was the sampling pattern at that site. Next site was at Traethgwyn. There's a large caravan park behind this site, and this is the one that had deteriorated in quality over about a 6-year period. Again, almost exactly the same pattern. Again, the red line represents river flow going into the sea, and it partly explains why you get the series moving up the pattern at times. But the variability, again, is very similar to Traethgwyn. We got here 1.9 log orders of magnitude, the average daily range, and 3.4 orders of magnitude is the maximum range. And that was the sampling pattern for that site. The last site we did was at Nolton in Pembrokeshire. So we were moving around the interreg less favoured area and to just select the most at-risk sites. And this one had a sufficient bathing water classification in 2017. But it was the worst good beach in Wales in 2018. So you can see it's been on the borderline between classes. Again, 3.9 log orders of variability as the maximum range, and 2. So 2 is 100-fold, and 3.9 is very close to 10,000. So this is the sort of pattern that we're now getting at every beach, and it's extremely variable. But more than that, it's very surprisingly variable when you think we only take at maximum 20 samples in the UK in a bathing season. And one of the things that this pattern shows you is that it's almost a luck of the draw, whether you are sampling during the peak period, and each vertical line represents 12 hours, or you just happen to be sampling lower down. But you can see again here, most of the samples, even for this site, during our sampling, most of the regulatory samples were really on the limit of detection at 10. But remember, the beach was one of these at-risk bathing waters, quite close in 2006 to into a failed condition. So that was the pattern we got. There was the sampling for Nolton Haven. And just to give you some idea of what we're talking about here, the different ranges, in terms now of a log 10 value, we'd have to do all the statistics in log 10 terms because the data is highly skewed for microbial data in beaches. But the mean in Swansea Bay, the daily range mean was 1.43, minimum 0.48, and the maximum 3.9. And there were 60 samples as an end value because there were 60 or 61 or 62 days this work was done. Chemist, very similar. Newquay, again, very similar. And Traethgwyn is, again, similar. So there's this kind of pattern of, emerging from replicate sampling at 5 beaches. So we're beginning to accept the fact now that David Kay, me, was wrong in the Swansea Bay case, because that's essentially showing the same variability now at 5 beaches. And I would say this is now proven in the UK as a generic pattern. So the conclusion of that element of the work, and I'm going to go on to some more modelling information. But the consistent within-day variation in fecal indicators, first observed in Swansea Bay, has been observed at 4 more beaches in Wales. It could suggest that such within-day variation is a generic pattern at UK beaches. And now, if it is, and it's the nearest thing we've got to ground truth, then it casts doubt on the utility of using compliance measurement of fecal indicator concentration to characterize water quality for a bathing day. And all the models that are used worldwide are using that assumption, i.e. that you take a sample on a day and it characterizes the concentration on the day. Now, this clearly proves it does not. Now, that is the basic modeling tool for agencies worldwide, including the US EPA, everywhere in Europe. Because what everybody is using is that single sample taken on a weekly basis for maybe 4 years in Europe. At best, it's using that as the modeling resource where they take that data and they model the inputs to the bathing water to predict that 1 day sampling point. And if that's not characteristic of the day, the modeling does not work. It also casts into doubt the fourth point, that the regulatory utility of compliance sample results should be reassessed, and it may not be the right way forward to regulate beaches. Okay, what might be causing the within-day variations? We know that some sites are highly diurnal. Swansea was in particular. There are 2 semi-diurnal aspects called tides, and we get 2 flood tides every day and 2 ebb tides. There are antecedent conditions like rainfall, temperature, etc. So in some sites, the intertidal morphology is particularly important, particularly where you get a long intertidal range and you have lots of time for sunlight penetration in fairly clear water. Other aspects like sediment resuspension, where bacteria do grow in places such as harbours in black cohesive sediments. These fecal indicator organisms can quite happily grow there, particularly the enterococci, which is the main European and WHO data to predict health risk. And there's also things like construction and maintenance and sediment deposition from dredging is another issue there. We've got new insights into predictive modelling because of the results that I've just outlined at these 5 sites. I'd just like to make a few points on this. The 2 papers, the one on the right is the WHO guidelines, which the EU standards were based upon, but the WHO recommends just the use of enterococci for marine waters, and the EU have kept with E. coli and enterococci because there's a lot of freshwater recreation in Europe. And where the way the standards were derived are outlined in the paper to the left. If anybody wants these, you can just use my university email and I'll send them to you. Sorry. The WHO suggests 3 risk levels. 10% risk of GI exposure is over 500 intestinal enterococci per 100 mils, but expressed as a 95 percentile. Now, in most UK waters, that means a geometric mean value of about 30 to 40. So the 95 percentile is the standard set by the European Commission. Sorry, by the European Commission and by the WHO. Substantial elevation in probability of gastroenteritis occurs at anything over 5%, which occurs at a 200 intestinal enterococci value as that expressed as a 95 percentile. And 1% is the sort of just perceptible risk issue where we have 40 intestinal enterococci as a 95 percentile. And this is the risk of gastroenteritis of a single recreational exposure. And that's the way the WHO derived their standards. And that's explained in a document called the Annapolis Protocol, which is free for download from the WHO. It was an expert group meeting in Annapolis, hence the name, in the US. And many people have used the approach in that document to underpin modelling. And the EU accept modelling as a way forward to discount and predict the high values and then take them out of the data set. And you get considerably better compliance, as we did at Aberystwyth Bay, when you treat the modelling in that way for prediction and discounting. Some of the work that underpinned that, we did this work in Wales, and basically this is Newport, Pembrokeshire. This is a livestock area draining the Pembrokeshire hills, and some sites, like the highly orange sites, were completely devoid of human habitation, but had lots of sheep and cattle. And on those orange sites, what that means is we got more than 1 million CFU, or colony-forming units, per 100 mils of the intestinal enterococci, which means it's about the same standard as a sewer, and that that represents the high flow data collected at those sites. So if you can predict that high flow, theoretically, you can use that kind of information to do real-time prediction of the bathing water quality if it's affected by rivers. Now, the US EPA experience in this area using compliance data was expressed in 2 reports in 2010. And what they said is they can model these sites, but they only get between 20 and 40% explanation of the variance at the bathing site. Now, given that you're explaining a health risk, they note that that's not really a very high level of explanation when you're trying to protect the public health. And that's certainly become realized over recent years. That kind of low explained variance is apparent right around the world with the modeling that's being done using the compliance data rather than the intensive data we've got. Now, why it's relevant, really, we realize this ourselves with the Swansea Bay experiments. And that was the Swansea data again, just to remind you, highly variable. And what you get at Swansea is it will basically fail in the morning, pass early afternoon, just pass sufficient, which is the lowest grade of pass, and it becomes poor again in the evening. And in Swansea, that means effectively that you could time your sample to go in the best water, or the agency could time their regulatory sampling to get the best water quality. But the US EPA recommend that you go for the poorest period. So there's some, I don't think any regulatory agency wants to adjust the timing to get the best water quality when people are maybe exposed to the poorest. This just shows the model, and you'll observe here the R-squared value is the explained variance of the Swansea model. And if you go, it goes on stepwise down the column, and it starts with the first variable, which is UV radiation on the sampling day, to 44%. It ends up at 80% when you put the 7th variable in. So it's a very accurate model at Swansea Bay, and that's improved. In its first couple of years, it improved the regulatory position to being just a bare pass to being good, which is 2 classes up. And you can draw this sort of through the bedding season. Blue line goes up and down every day, and that is the predicted bacterial number. And the peaks are during the night time, as you might expect, because the sunshine acts to kill the bacteria. And that means effectively you can do real-time prediction through the bathing day. The actual data as geometric mean values are the orange diamonds, which in this case now means geometric mean values of the data we've got. So that stays on the line, which is how it should be. Just to take you through very quickly the remaining 4 sites, Chemice Bay water quality, and the model. Well, we've got a model here with 6 predictors, and at the bottom of the table, that model has a 76.3% explained variance. That shows the data plotted up going through the bathing season at Chemice. Next one, Newquay North. This now has on the second column from the right, we've developed a series of models, and this is our worst case so far. We only get 57.5% at this site, and we know why. It's affected by an urban drain that we couldn't actually get measurements into. So we've not got measurements into one of the main sources of bacteria. But 57.5 is still a lot more than the 40% the US EPA have been achieving. Next one, Trithe-Gwyn. And we now back up with the model. On the left-hand side, it says 9 half day, and that's the, it says 1 half day, and that's 79.1% again, which is, again, pretty good. And then the last, there's the prediction through the bathing season. And now at Nolton Haven, we're now back up to the 81.3 and 81.2% models. This shows a number of modeling options that we're choosing with the local regulators. So there's the through the bathing season plot, and some questions. What this indicates and what it asks me as a scientist, and I've been working in this area since about 1980, is the WHO assumed standard deviation on confirmed intestinal cocci concentrations more credible? Yeah. The WHO on their standards assumed 0.8, and we're getting somewhere between 0.85 and 0.65. Can we predict as per Annapolis reliably? I think the answer is now yes, definitely. We're getting very high explained variances for any model. Then next question, prediction and discounting as per Annapolis, does that work? I think now the answer is yes, because we're getting much better than 20 to 40% explained variance. And is real-time within-day beach management as per warnings of adverse tidal conditions by lifeguards now possible? The answer is yes. And can such routine predictions replace regulatory sampling for considerable periods? I think again the answer is yes. If your sample for regulation is collected, you know the result 3 days down the line. Therefore, it's not protective of public health or a feasible means of protecting public health, but the real-time within-day prediction can be. And what we've been advising in the recent revision of the Bathing Waters Directive is that we turn completely to modelling and possibly revise it once every 5 years, but then that you don't use regulatory sampling for the modelling exercise. Thank you.